Hi, Natalie. All right. Well, I'm going to get started. Well, first off, are there any questions that you have?
I did have a question.
Okay.
On number 10 on the review.
On the pretest?
Yes.
Let me pull that up. Yes. Now, number 10, which part did you have a question on, or was it the whole thing?
I just wanted like you to go over that problem.
Okay. Well, here, let me draw it out. Let me see here. Switch pens here real quick. It's just about like that. So it should be about -3 and 8. -3, -8. Let's see. -4, 5. And -4 and 2. Right up to 5. So with this problem, what we're going to be asked to do, so we're asking for whether these one-sided limits. And the thing with the one-sided limits, the first problem is asking, what's the limit of f of x? And this here, the purple here is the f of x, kind of a interesting little function. And the first question is asking, what's the limit of this function as x approaches -8 from the right? So that means you're approaching -8 from this side. And that's what that plus means there. The minus in front of the 8, between the arrow and the 8, that just is there to indicate -8. But then you have a plus sign. And what that's saying is we want to be on the right of -8. So as x approaches -8, but from the right side, what's the value of this function? Where's this function headed to? And the closer we get to -8, the function's getting to closer to -3. And so that's what's going on with this one. Now, does that make sense?
Yes, that helped.
Now, if we take a look at x approaching -4, now it's -4 minus. What we're being asked to do here, here's -4. We want to approach -4 from the left. As we do that, the function is rising up to 5. So for this one, the limit's going to be 5. Now, if you approach -4, though, from the opposite side, if you approach it from the right side, to the right of -4, the function's at 2. So we do this. So approaching -4 from the right, we're going to get 2. Now, the next limit asks, okay, so you've got the one-sided limits for x is -4, approaching from the left, approaching from the right. But what about what's going on in general? In other words, if x is just approaching -4, what's our limit going to be? And it's like, well, what do you mean? It matters if you come from the left or from the right. And because that matters, there isn't a general limit. To answer any questions about limits for f of x, we have to specify a right side or a left side. There's no general limit here. So what this says is this limit does not exist. So that one's going to break down. That one's not going to work. Now let's see. I'm going to take a look at this other one. Now, for 0, though, if we approach 0, and again, if we approach from the left, well, the value of our function is 2. Likewise, if we approach from the right, well, we're still going to have a function value of 2. So now we ask the question, do we have a general limit? In other words, as x approaches 0, regardless of the direction it takes, what is f of x converging to as an f of x value? And whether you go from the left or from the right, you're going to converge to f of x equals 2. So any questions about that?
No, thank you.
No problem. It's the same thing as x approaches 3. Exact same thing. So the limit as x approaches 3 from the left, and we use the minus for left and positive for right. Again, it's going to be 2. Because as you approach here, you're around f of x is 2. Now, we're not asking about the function value at 3. We're approaching 3. So as we're near x equals 3, we have function values of 2. And same thing if you're approaching from the right. So because the left limit and the right limit are both equal to 2, the general limit will then equal 2 as well, just like with 0. Now, the last one, as x approaches 6 from the left, for this one, when you're just to the left of 6, you're still hovering around f of x equals 2. So you're going to have that. But if you were to ask the question, say, what's the limit if we approach from the right? Well, there's no domain here, so this limit doesn't exist. And therefore, you can also say that the general limit doesn't exist also. So all we have is this approach from the left. It's the same thing that happened over here as x approaches -8. We can only approach it from the right. There is no approach from the left. That doesn't exist. And that also means the general limit, only the one-sided limit's going to exist. So does that answer your questions?
Yes, it does.
Did you have any other questions?
No, that was my main one.
All right. Well, what I'm going to do this evening, I'm just going to do really just kind of a couple problems from, say, each section. If any questions, let me know. I'm recording the session, so I'll post the results on the YouTube channel. And that's going to be pretty much it. If there's any questions that come up, let me know. If for some reason you need to leave the session, that's okay. I'm going to keep going, and then I'll post the recording. So first off, what comes up in section 2.1, what you probably want to know to do here is the difference between an average rate of change and an instantaneous rate of change, or finding the slope of the curve at a single point, or what we would call a tangent slope. So say you have something like this. So if you're looking for and let's say we're looking on this interval. Say on the interval 2 to 3. And so let's say we want the average rate of change on this interval. So what you're basically doing is you're calculating the slope of a line as it passes through this point in this point, or the point that we get when x is 2 and the point we get when x is 3. So what you can think of, that's your x1 and that's your x2. And then y equals 7 minus, let's go with x1 first. Well, with x1 goes a y1. And then for y2, And that's your y2. So to get the average rate of change, what you're going to do is calculate the slope. And if I'm going too fast, if you're taking notes, just let me know. I can slow down. So we're going to get -5. So that's all what the average rate of change is. So any questions about the average rate of change? So the next thing we might ask about this is the slope and we're going to choose the point 2, 3. So this is no longer an integral. This is a point. In the text, they'll put a P like that to indicate a point. Now this we have to use a special formula. For this type of question, this is the formula you're going to use. So in this case, our x is going to be that 2. So we'll get the limit as h goes to 0, 7 minus 2 plus h squared minus this here, so we're going to get -7 plus x squared. Minus and minus becomes a positive, divided by h. Foil this. Oh, I'm sorry. Let me go back here. We know what x is. X is 2. So this is going to be a 2 squared. So we're going to get -7 plus 4. And then the minus sign will be distributed. And again, that x squared up here was really a 2 squared, which is our 4. So that's going to give us, let's see here. So these will cancel. We can factor out an h. And then with that factored out, we can cancel. And so that'll give us the limit as h goes to 0 of -4 minus h. Well, at this point, we say h is going to be practically 0. So that, for all intents and purposes, is going to be this. And that's going to be your answer. So any questions about that? All right. So that's going to be something you're going to want to know how to do. The difference between an average rate of change and the instantaneous rate of change, or as it's sometimes expressed, the slope of a curve at a single point. So one of the things we encountered were the limit laws, and this is like the limit of a product is the product of the limits, and the limit of a difference is the difference of the limits. And this makes calculating limits pretty versatile. So let's say we have this. So we have something like this. Well, using our limit laws, and a good summary of those laws, let's see, page 61. But what this is going to say to start is that we can distribute, so to speak, our limit So we're going to get something like this. And what we're going to have our constant can pass through here. So just bringing that constant through. And I'm going to skip ahead a little bit. We can get a little pedantic with this, like we can move the limit inside the x squared, so it's the limit of x, and then that limit is squared. But I'm just going to cut to the chase. You can also do this. We can put the substitution right here. And the limit for a constant function, the constant function is going to be the same. So -4 plus 10 minus 2, or this is going to be +4. So any questions about that? So that's pretty much just a substitution. Now let's take a look at some that are a little trickier. You can get some that are interesting. Yet the one advantage we have with limits is that we're free to do cancellations. Now, if we look at this, we could say, okay, well, I know the limit of a quotient will be the quotient of the limits. So that means I could just substitute 5 in for x. But if you do that, you're going to get a division by 0. And that's not going to work. So we can write if x minus 5, and this will be x minus 5, x plus 5. This, and this is again, this is where in calculus you get to do that algebra review. This is a difference of squares. And that's going to be equal to, well, what we have down here. Or to put it another way, a squared minus b squared, a minus b, a plus b. So there you go. Again, what are those things from algebra? So next, we're going to cancel the x minus 5. And that's going to take away that situation with division by 0. Now, again, when you're working in algebra, if you have a function that's given to you like this, as far as domain and range go, you specifically domain, actually, you got to leave it as it is. But when we're dealing with limits, we can cancel things. And that's going to set us up for this. And this will be 1 over 5 plus 5, or 1 over 10. So that is something to keep in mind. You might have some cancellations you have to address. Say, like, let's take a look at another one. So any questions about that one? So a tricky one would be something like this. This is kind of another one of these problems with an algebra trick. So what you can do with this, you can rewrite it x is square root of x squared, and 9 is 3 squared, or square root of x minus 3. So once again, we've got a difference of squares. So we can break it down as a minus b, a plus b. And again, we can do some cancellation here. And this isn't going to be a problem. So we'll do our substitution. Square root of 9 plus 3. 1 over 3 plus 3. Or 1/6. And that's going to be it. Any questions about that one? Now, there are other kinds of cancellations, not just a squared minus b squared. So once again, if we substituted for x, we're going to get a division by 0. -5 plus 5 is 0. But this right here, we can factor this. Use our guess and check method here. So we need an a and a b that adds up to 3 and has a product -10. And an a and a b that will do this, let a be 5, let b be -2. And that'll let us factor this quadratic into this. Our +5 and our subtract 2. So this is going to help us out a lot, because if we're going to get x plus 5, x minus 2 in the top, this and this, they're going to cancel. And again, if I'm going too fast, let me know. So we've got our cancellation. We'll get -5 minus 2 or -7. And that's going to be our answer. Any questions about that? So let me show you another one that can, a little interesting. Not a little algebra tricks in this section. Now, if you substitute x as 0, you're going to get 0 divided by 0 ultimately. So we want to at least prevent a division by 0 in the denominator. And what we can do is we can factor out x squared. And we could do the same on top. So we'll get some cancellations. And so now we have 5x plus 8 over 3x squared minus 16. Now if we substitute 0, we're not going to get 0 divided by 0. We'll get 5 times 0 plus 8. 3 zeros squared minus 16. Well, that's 0, and that's 0. So we're just going to get 8 over negative 16, or negative 1/2. And that's going to be our answer. So any questions about that one? So let me do one like this. There are some of these that have square roots where what we want to do is rationalize to take the limit. So let's see here. Let's say we do we have this one like this. Now, once again, if we substitute -1 in here, we're going to get division by 0. So a technique we can do, we can rationalize. That means we'll multiply top and bottom by the square root of x squared plus 8 plus 3 square root of x squared plus 8 plus 3. So the original problem is this. And to solve this problem, we're going to multiply by this. So when we do that, and we could take a look at this, we'll get this times this, the square root will go away, x squared plus 8, plus 3 square root, minus 3 square root, so those will cancel. And then -3 times 3 is -9. Now on the bottom here, it's going to be a little more complicated. X times the square root and then we'll have x times 3. I'm just foiling these is what I'm doing, though. It's one heck of a foil. Then 1 times the square root, which is just the square root. And then finally, 1 times 3 is plus 3. All right. So let's see. Kind of a messy one here. Any simplifications? Well, we can, well, not too much we can do on top, we'll get something. But let's substitute in this -1. And 8 minus 9 is -1. We have -1 square root -1 squared plus 8 plus 3 times -1 plus minus 1 squared plus 8, taking the square root of that, and then plus 3. Let's see, it doesn't look like we're improving anything yet. Let me take a look here if I made a mistake on our approach. Let me see. Yeah, that makes sense. It'd still be 0. That's not going to change anything. Let me see. Yeah, that would actually not work. Oh, okay, so here it is. Let me back up before the substitution. So what's going to happen, let's not get too carried away just yet. So I'm not going to FOIL the denominator just yet. All right, and I'll show you why. So we're going to FOIL the top part. The square root times the square root goes away, leaves you x squared plus 8. Square root, positive 3, and you have a square root and a negative 3. It's all going to cancel. So you still have x squared plus 8. And then finally, negative 3 times 3 is going to be negative 9. And that simplifies to x squared minus 1. We're going to keep our x plus 1. X squared plus 8 plus 3. Now, something to see with this problem. The issue with this problem from the beginning was this denominator. Because as x goes to minus 1, get negative 1 plus 1, you're going to get division by 0. So we want to cancel this. So since we want to cancel this denominator, let's not FOIL this and this just yet. Let's just keep them intact because we want this part to disappear. Where we're going to get help is in this numerator. And I'll just be complete on this, just in case it went too fast. This times this would give you the x squared plus 8. This and this is the plus 3 square root. This and this is the minus 3 square root. And then this and this is the minus 9. So these are going to cancel. We'll get 8 minus 9 is negative 1. And again, the reason I'm not going to FOIL the bottom here, because at first it might not seem why not? We FOIL the top, why not FOIL the bottom? Again, we want this to cancel out because this is the problematic term. So we're going to keep that term around. And hopefully we get something in the numerator that's going to cancel out with it. And sure enough, this is a difference of squares because 1 squared is 1. So we had our cancellation, and now we have this. And now we're not going to have that division by 0. So we substitute our -1. Or -2/6. And that's going to reduce to -1/3. And that's going to be our answer. Questions about that? So let me do one more that's like that. We'll go in, we'll hammer another one of these through. And again, we're going to look for that denominator to cancel. So let's say we have one like this. So again, the issue is going to be, as x becomes 2, we're going to get 2 minus 2, or division by 0. So we're going to solve this by multiplying top and bottom. X squared plus 12 plus 4. So if this was a plus, we would make this a minus. Because it's a minus, though, we're going to make this a plus. And again, we're going to want this to cancel out. So we'll FOIL on top, but not down below. So the square root and the square root will just give you x squared plus 12. Square root times 4, or 4 times the square root, minus 4 times the square root. We're going to get that cancellation again. So that's going to be 0, but I'll write it down. Let's take a look at this. Again, the advantage with calculus is it gives you a great review of algebra. And then -4 times 4 is minus 16. But on the bottom, we're not going to FOIL, because that x minus 2, that's the term giving us all kinds of trouble. We're going to leave it there. Hopefully, we're going to see something that will cancel it out. So as we simplify the top, Let's see, 12 and negative 16 would be minus 4. And once again, we're going to get a difference of squares. This is a plus 4, believe it or not. 4 is 2 squared. So we're going to get and that's going to give us the cancellation. So we'll have x plus 2 over the square root x squared plus 12 plus 4. And taking a look at this, we're not going to get a division by 0. We're not going to get 0 in the bottom. So this will be the square root. 2 squared is 4, so that's going to be 4 plus 12 plus 4 over 2 plus 2. Or square root 16 plus 4 over 4. Or 4 over 4 plus 4. 4/8. Or 1/2. And that's going to be the answer. So any questions about that one? So this trick, this rationalization trick, it's also going to hold true if you have to do something with the denominator as well. Let me do one more, and then we'll move on. But there's another kind of problem like this you can see. Now for this one, if you put 4 into x, 4 squared is 16, 16 plus 9 is 25. Take the square root of 25, that's 5. 5 minus 5 is 0. So we're going to solve this problem the same way. We're going to multiply by 5 plus square root. And again, if this was a plus, we would make this a minus, but because it's a minus, we're going to make it a plus. Now, what makes this one interesting, for this one, we are going to FOIL the bottom. We are going to do that. So we're going to FOIL the top and bottom. 4 times 5. Well, hold on. Let's see here. Let's FOIL the bottom first. We'll get 25 minus 5 square root x squared plus 9. And then this and this will be, let's see here. Oh, this is a positive. The inner one will be a negative. And then square root and square root, make that go away, but you have a positive and a negative. We get negative x squared plus 9. So for this one, where we have the square root in the bottom, and this is where we're getting the 0, for this one, we are going to FOIL. And then the one on top, let's leave this. So looking at the bottom here, these are going to cancel the plus 5, the minus 5. So we have 4 minus x. So we've only FOILed the bottom. And this will be 25 minus x squared minus 9. And then 25 minus 9. Well, that's going to be 16. Ah. Now we're still seemingly in trouble here, because if you put in the 4, you got 16 minus 16 is 0. But this is 4 squared, this is x squared. We have a difference of squares. A minus b, a plus b. And sure enough, the problematic part, it's going to cancel. And so what we're going to get is the limit as x goes to 4 plus x over 5 plus square root x squared plus 9. No danger of any division by 0. So we're going to substitute. So 16 plus 9 is 25. 4 plus 4 is 8. So we get 5 plus 5 over 8. That's 10/8. And then it reduces to 5/4. So there's a lot of these little tricky problems in this section. This is 2.2. But I just want to go over at least some of the sort of the trickier algebra situations you're going to encounter. All right. So section 2.3, this is where we deal with limit proofs. So let's take a look at one of these, or maybe one or two of these. Again, if I'm going too fast, let me know. Let's see here. So let's say we have this. So what we want to do is we're looking for a delta value. And basically what we have is a situation like this. If this is in fact true, then for any epsilon greater than 0, there's delta greater than 0, such that the distance from x to, this is c, the number x is approaching, when that distance is less than delta, then the distance between f of x and the limit will be less than epsilon. So basically, if we get x close enough to 3, or the distance between x and 3 is small, then the distance between f of x and the limit is also going to be small. So this is arbitrary. We get to make this as small as we want. So let's try to find the delta. If we want to get 3x minus 7 as close to 2 as we want, then how close does x need to be to 3? So let's find that delta value. So we're going to start off with f of x minus L is less than epsilon. Epsilon is some tiny, tiny positive number. So for us, so it'll be 3x minus 7, that's our f of x, minus our limit of 2 is less than epsilon. Or we could do some combining in here. Negative 7 minus 2, it's going to be 3x minus 9 is less than epsilon. And we can actually factor a 3 out of this. So we get 3x minus 3 is less than epsilon. Or the absolute value here, 3 is a positive number, we can pull it out. Absolute value of 3 is 3. And then divide by 3. So what's significant about this? Why am I stopping here? Well, let's note that the absolute value of x minus c less than delta is going to be x minus, and c was 3. So what this says is that delta and epsilon over 3 are going to be the same thing. So what we have here for any epsilon greater than 0, there's delta equal to epsilon over 3, such that when the distance between x and 3 is less than epsilon over 3, then the distance from 3x minus 7 and 2 is less than epsilon. And so if we want our function with an epsilon units of 2, we got to have x with an epsilon over 3 units of 3. Questions about that? Oh, right. Oh, and just to mention that if we had 3x plus minus 9 was absolute value of 3 times x minus, or the absolute value of x minus 3. So you can factor that out. And you could do the same thing if you had like a negative. This would be plus 3 here. Like this would be 3x minus 3. This would be 3x plus 3. But anyway, just a little review with absolute values here. All right. So that's one way of doing these. There's another technique we looked at, though. Let's say we have this. So we've got something like this, and we're actually going to solve this one a little bit differently. So again, we're going to have an epsilon greater than 0. And so we want a delta greater than 0 such that x minus c less than delta, then f of x minus L is less than epsilon. We're looking for the same thing. So we're going to start out the same way. So f of x minus L less than epsilon, or square root of 4 minus x minus 2 less than epsilon. Now, for this one, we can break things up. You get minus epsilon. And this is something we can do to get rid of those absolute values. A little trick you can use. And then we can add the 2 to both sides. And then we can square everything. Let's see. Right, this is 2 minus epsilon squared. If we square this, let's see, we'll get 4 minus x, 2 plus epsilon squared. Let's see here. Now this is a little tricky. We can multiply through by -1. because this is going to be problematic. Let me subtract 4 from both sides first, which might look a little strange, but let me bring this up. What I'm going to do is I'm going to solve for x. Now this is a negative x, and I want to make it positive. So I can do that if I multiply it by -1. But I multiply by -1 here, the multiply by -1 here and here. The whole thing will be times -1 times -1 times -1. And because I'm multiplying through by negative, it's going to switch around these. We're going to get this. All right. So I'm just going to rewrite this so it's 4 minus 2 plus epsilon squared less than x less than 4 minus 2 minus epsilon squared. Let's see. So let's take a look at this. Now, I admit this is kind of a tricky one, but I might be doing this the hard way. Let's see. Let's take a look. So we're going to have x somewhere in the middle. Now, here we have 4 minus 2 plus epsilon. Okay, it's squared. Now, what might help us here is we can try to FOIL the 2 plus epsilon. Let's see if that's going to help do some cancellation. It will make this a little easier. So 4 minus 4 plus 4 epsilon plus epsilon squared. And this would be 4 minus 4 minus 2 epsilon plus epsilon squared. So we get 4 epsilon plus epsilon squared. And then we have, oh, this is a minus 4 epsilon. Oh, but then the minus and the minus becomes a plus. We have 4 epsilon minus epsilon squared. Let's take a look. And this one also has the minus and the minus. Let's see. Just double check. Minus, and this will be minus, minus, and minus. All right, so let's see here. Not seen yet. So let's take a look. So we have x between these two. And again, I'm wondering if I'm doing this the hard way. I didn't make a misturn somewhere along the way. Let me see here. There's a better way of doing that. All right, let's see. Well, let's stick it out. Let's see if there's something that simplifies here for us. Let me just double check my sign, make sure I didn't make a mistake on one of those. That's right. So let's see. Put another line here. That's probably not going to help us. Looking. Pardon me. So I might have gone off a deep end here, and I'm concerned that I might have missed a sign. So I don't want to waste too much of your time fiddling with this. Let me show you. This is actually not the one I want to show you. I want to show you a different one. So what I'll do this one. Let me come back to this one. I can post a video on this one. The one I want to show you is actually more along these lines. I'll come back to that one. I don't want to chase down a rabbit hole and use up your evening. But let's say we have something like this. So let's say we have something like this. And what they want us to do is, again, calculate a limit. Now, in this case, epsilon is given. So for this, and so for this one, we can break it up. We can do this. So this is the one I actually do want to show you. Just for completeness sake, I'll come back to that other one. But this is the other technique I actually want to show you. So this is where you can break things up like this. And in this way, let's see if we add 1 to both sides. We'll get this. Now, if we square everything, we're going to get this. And then I'm going to subtract 1 from both sides. So that's going to be 0.19, 0.21. So this is where we're going to take a look at a picture of our interval. Now remember, we're approaching 0. Exaggerate this a little bit. So what we're finding out with an epsilon of 0.1, that's going to place our x between negative 0.19 and 0.21. So we could actually choose a smaller value for the upper bound of 0.19, and we're still in this whole interval. So we'll just be a little more strict, and we'll go for that. So now we'll do this with x. Negative 0.19 less than x less than 0.19. So let's talk about delta. Note. So you have x minus c less than delta. Again, you can break up the absolute value like so. Now c is 0, so that means we're looking for something like this. And wouldn't you know it, there we go. So what this means is that delta equals 0.19. And so that's going to give us our delta. So now we can go back. We can restate our proof. So for epsilon as 0.1, there's delta equal to 0.19, such that an x minus 0 is less than 0.19, then square root x plus 1 minus 1, which was our limit, is less than 0.1. So this is the other type of limit I wanted to show you. The first limit with the 3x minus 7 is our function. There's that one, and then this one. Now, for completeness sake, I'll go back and do that other one. I'll hammer that one out and I'll post it. But the first limit and this one, these are the two that I would really recommend being familiar with. And I'll go back and do that other one. I want to make sure I didn't make a mistake or choose a a wrong path, a more complicated path. Maybe not a wrong path, but maybe not a helpful path. So I'll get back to you on that one. So for one-sided limits, we saw some one-sided limits at the beginning, Natalie, with your question. And that would be a type of question I would ask. I do want to go over some computational ones. So let's say we have something like this. So for one-sided limits, we basically substitute just like for our standard limit. And in this case, there's no issues with division by 0. So what that's going to give us, we can substitute in. We'll get 1 minus 1, and then 1 plus 2. And this is, if you want to get technical about it, which is a good thing to do in calculus, this means we're to the right of 1. So we're dealing with numbers bigger than 1. So even though I'm substituting 1, technically this is a slightly bigger number than 1, but it's only slightly. So practically speaking, this number minus 1, the difference might as well be 0. So we get 0 over 3, square root of 0, and that's just going to be 0. So again, you're just going to substitute. Now, there are situations, though, where you could get some interesting results. And let me show you this one. And it does matter. In that one, it didn't matter if we approached 1 from the right or from the left. We were going to get the same answer for all intents and purposes. For this one, though, let's take a look. Now, I do want to say on that last one, in some ways, it does matter if you approach from the left. And here, let me back up here a little bit. I do want to give a little commentary on this. There is an issue with this one. I said it didn't matter if you approach from right or left, and that's how it looks computationally. But actually, there is a problem. Because of the square root, if we had something like this, and we tried to compute this limit, when we talk about domain, the domain for this function, we need to make sure we're dealing with x values so we keep this greater than 0. So what's definitely going to be an issue if we're dealing with negative numbers that are, or dealing with numbers that will make this negative, we're going to be outside the domain. So technically for this one, I'm getting kind of a little, I just want to correct a misstatement that I made there. For For this one, to the left of 1, we're not really going to have any domain available. And that's something that we do need to be careful of. Now, we'll get some domain back. For example, if you did say, actually, no, you wouldn't. You would lose it. You're still going to lose it. No, you get some domain back. You do get some domain back. For example, if you let x be -10, you'll have a negative. You have a -11 divided by -8. That'll be positive. You can take the square root. But my concern, like for example, if you let x equal, and I'm going on a tangent here, but I just want to correct a misstatement. If you have the square root of 0.5 minus 1 over 0.5 plus 2, you're going to find yourself with -0.5 over 2.5. And since we're only dealing with real numbers, we can't take the square root of this negative. So for domain values just to the left of 2, something like just to the left of 1, we actually don't have a limit. We're not going to be able to take a limit there. So for this one, we can only take the limit to the right of 1, not to the left of 1. So that was a misstatement. I apologize. Only to the right of 1. But as long as we have domain available, and here I'll do one where what I'm getting at, as long as we have a limit where we have a domain that lets us take that limit, well, then the substitution with one-sided limits is not going to be any different than two-sided. So if you have something like this, there's domain for this function to the right and left of 2. So we can just substitute. And so we're all good. And you're going to get the same thing computationally. If this was 2 minus, you're going to do the same thing. The reason we can be so cavalier with this is that with 4x plus 3, well, as we approach 2 from the right or for the left, we're converging in the same location. Where you've got to be careful with these limits, though, one-sided limits. You want to watch out for, say, something like this, where you're going to get that jump. Or just like that other example with the square root, you want to be careful with something that has a domain that stops, say at x equals 1. We do have a right side limit, but we don't have a left side. So we want to be careful of that. And sometimes it doesn't hurt. It doesn't hurt when working with one-sided limits. Get a sense of what your domain is. Get a sense of what the domain is and if there's any jumps or anything like that. Like in that first question, Natalie, that you had asked. So you do want to be a little careful. You do want to be careful. You don't want to be too cavalier. So let me give you another example of this. And this is one I wanted to show you. Now, this one's not going to be so much a domain issue. Now, we're approaching -2. So we're approaching it from the left. Here's -2, -3, -2.5. We're dwelling in this area. So what this means is this. when we're picking numbers from this side of -2 and we're adding them to 2, this part's going to be negative. And this part will have the same magnitude, but it's going to be positive. So like, for example, say it's -2.5 plus 2 over -2.5 plus 2, we'll get -0.5 over -0.5, or 0.5 over -0.5, or -1. So this we can do cancellation, but because we're approaching from the left, and we can use a number to the left of -2 as a test, like -2.5, that means the cancellation, so we avoid a division by 0, is going to be this. We're going to get a -1. Now, if you graph this function, it's got no jumps, no skips, and its domain is the entire x-axis, so we don't have to worry about missing a domain, say, to the left of 2, or -2 rather. So then this one we can just substitute once we've cleared that. And that's going to be our answer. Now, let's take a look at the same problem, but approaching the right of 2. So any questions about that? The right of -2. So now, here's our -2. Here's -1, -1.5. Now we're dealing to the right. So we're talking about this. So to get an idea what's going to happen here, choose one of these numbers, say -1.5. Well, this will be the absolute value of 0.5 over a positive 0.5, or 0.5 over 0.5, or 1. So if we just substituted -2 in here, -2 plus 2 would be 0. So we're looking for a cancellation, but this will become a 1 instead of a -1 like last time. So we're going to get this. And so now we can just substitute, because again, there's no jumps or breaks, there's no gaps in the domain here. So we -2 plus 3, which is going to be equal to 1. And that's going to give us our answer. So any questions about that? All right. So looking at 2.5. So a question that I would look at for 2.5, one I would be really interested in. Is something that we ask about what kinds of continuity do we have, or do we have any continuity at all? So let's say we have our Cartesian plane here. Say we have something like this. We'll call this A, B, C, and D. And so what kind of continuity are we looking at? Well, let's keep in mind what continuity is. There's different types. First off, take a look here. There's the left continuity. And so for that means that f of c exists. And then the limit as you approach C, and you approach it from the left, exists. And then this limit as x approaches C from the left of f of x equals f of C. You'll have something like that. Now for the right, and just for the sake of time, I'm just going to kind of truncate this. We'll just say relabel this as right. For right side continuity, f of c exists. The limit approaching from the right exists, and the limit approaching from the right equals f of c. Finally, when we say something is simply continuous, f of c exists, the double-sided limit exists, and the double-sided limit equals f of c. So let's take a look at this function that we have here. So for point A, first off, it exists. We do have that. And we have a limit coming from the left. And the limit from the left will equal, well, we'll call this A, we'll do it this way, f of A. So the limit we can take comes from the left, and it's going to be equal to f of A. So since it from the right, it's approaching from the right. So this is going to be right side continuous. Now for B, f of B exists. That is true. But the limits, if we look at the limit from the right, or approaching from the left, approaching from the left, the limit approaching from the left equals f of B. The limit approaching from the right doesn't. So this one is going to be left continuous. Now for C, f of C exists, and the double-sided limits they exist and they equal f of c, so c is going to be continuous. Now d, f of d exists. There's only one limit we can take, and that's coming from the left. But this limit does not equal f of d, so this one's discontinuous. So any questions about that? I'm going to put in another one. Let's say we have this. E. Well, the problem with E, the left side and the right side limit are equals, and they do exist, but f of E doesn't exist. So once again, we have a discontinuity. So any questions about that? All right. So the last thing to look at, it's going to be infinite limits. So let's take a look at this. Let's say we have the limit. Let's see here. As x goes to infinity of 2x to the fourth plus 5x squared minus x plus 6. And then we have 9x to the fourth plus x. So what we can do, we can divide everything by x to the fourth. And so that's going to give us, on the denominator, we have 2 plus 5x squared over x to the fourth minus x to the fourth plus 6 x to the fourth being divided by x to the fourth. This will be 9 plus x over x to the fourth. So now we're going to simplify. So we'll get 9 plus 1 over x cubed, and then 2 plus 5x squared minus 1 over x cubed plus 6 over x to the fourth. And so what's going to happen as x goes to infinity, or if x went to negative infinity, you're going to get the same result here. This will go to 0, 1 over x cubed. This will go to 0, this will go to 0, and this will go to 0. And so what you'll be left with is the limit as x goes to infinity of 9 over 2, which is just 9 over 2. And that's going to be your answer. Questions about that? All right. So let's take a look at another one. Now, when we're dealing with these, a question like this, if you want to do, you can see where there's going to be a division by 0. So we're going to have some trouble, so to speak, when x is equal to 7. Well, sure enough, that's where x is trying to go. So one thing you can do with this, sketch a little graph. Now this is one of the canonical functions, 1 over x squared. And it looks like this. And then what we can do is shift it over to x equals 7, like so. And then if you multiply by 4, this is just going to stretch it vertically. It's really not, for our purposes, for taking a limit, it's not going to really have any significant effect, but it will stretch it vertically. So now that we know what this looks like, let's take a look at this limit. Now, they're asking for a double-sided limit. So as we approach x equals 7 from the left, we're going to get infinity. And as we approach it from the right, we're also getting infinity. So this means the limit as x approaches 7, x minus 7 squared is equal to infinity. So any questions about that? All right. Let's see. So for those, that's what I would recommend. You can use test points. You can plot the graph using just picking some x values, generating some f of x values, and that would help as well. Let's see here. And let's do another one. Let's say we have this. Something like this. Now again, this is a canonical function. It's going to be your 1 over x, and it's going to look like something like this. So here, and this is at x equals 0, this is where you have your asymptote. So if you're approaching from the left, you're going to get negative infinity. If you're approaching from the right, you're going to get positive infinity. So we're multiplying basically by 1/3. So just kind of makes it a little more, kind of brings it a little closer in here. But you can still see, since we're approaching 0 from the right, we're going up to infinity. And so that's going to be our answer. And of course, if you did something like this, if you approach from the left, now you're dropping down, you'll get negative infinity. So any questions about that? All right. So I think for the review, that's pretty much it. I'll go back over that one limit, the proof problem there. And I might post something also about that square root with the one-sided limit, just to emphasize the issue with the domain not being there. And that's something that with one-sided limits, you do want to check for whether or not the domain exists to the left or to the right of something. And then keep in mind, keep an eye out for what's going on with like vertical asymptotes, jumps or breaks and stuff like that. But that's going to be it. If you have any other questions, let me know. Other than that, have a wonderful evening.
Thank you.
No problem.